Hi, Year 12. This is our last lesson for the topic of differential equations. In this lesson, we're going to look at modelling differential equations. So this is what we've covered so far. What are differential equations? Then we looked at slope fields, independent variable questions, dependent variable questions, and then last lesson we looked at separation of variables. So this is what we're going to cover. Exponential growth and decay, Newton's law of cooling, logistic equations, and conserved quantities. All right, let's start with exponential growth or decay. It occurs when there's a direct variation between the rate of growth or decay and the size of the quantity itself. Now, you may recall doing direct variation back in Year 10, but if not, let's go through it again. So, direct variation between the rate of growth or decay and the size of the quantity itself means this. Here's our rate of growth or decay. It's proportional to A. Now, this is a linear relationship. In fact, we can rewrite this as dA dt is equal to Ka. It's like y equals mx. And direct variation, that's what this means. It is a straight line relationship that goes through 0, 0. All right, back to our differential equation here. If we want to solve this, we want to take integrals of both sides with respect to a, so we need to invert both sides. And so t is equal to 1 on k, that's a constant, so I've brought it out the front, integral of 1 over a dA. Now that's a simple integral, it's just ln a, and don't forget your constant. All right, now to finish this off, we want to make a the subject, so let's move c over the other side and multiply both sides by k. Raising both sides as powers of e, I end up with this. Now we could leave it there, but I'm going to show you a little trick. I'm going to expand this out. It's the same as e to the kt multiplied by e to the negative ck. Now this is just a constant, but it's a really complicated looking constant. So I'm going to rename it, and I'm going to rename it as a naught. And there's a reason why I'm doing that. Let's have a look what the size of the quantity is at time 0. So substituting in t is equal to 0, I get a naught, e to the 0. And of course, anything to the power of 0 is 1. And so this is the size of the quantity at time 0. So here's the solution to our differential equation. Now, there's one more thing I want to tell you. If k is greater than 0, then this is exponential growth. If it's less than 0, then it's exponential decay. Here's an example. Carbon-14 decays at a rate proportional to the amount remaining. In other words, dA dt is proportional to A. It has a half-life of 5,730 years. Find the constant rate of decay. All right, you need to know that carbon-14 is present in all living things, and the minute that a living thing dies, it starts to decay. Now, after 5,730 years, half of it remains. All right, so from here, we can rewrite that as this and then solve our differential equation and end up here with a solution. Or you can start here. But a word of warning, this is not given for you on your reference sheet. So if you want to recognize this question as an example of exponential decay and start here, you're going to have to memorize this equation. I'm going to start here. So we've got a equals a naught e to the kt. We need to figure out what a naught is and then what k is. Now we don't have a lot of information, do we? All we know is that after 5,730 years, half of the carbon-14 is left. But half of what? So a bit of a trick. We're going to make a naught 100%, or 1. So let's substitute in. Have a look at this. Half of it's left after 5,730 years. And I've made a naught equal to 1. Hope that makes sense to you. Take logs of both sides. I've turned that around. Divide both sides by 5,730. And k is approximately equal to negative 0.000121. Right, a quick check. It's a rate of decay. It should be negative. Now, a really good example of carbon-14 decay is the Shroud of Turin. Now, the city of Turin is in Italy, and it's famous for a linen cloth that is alleged to have covered the body of Jesus Christ during his burial. You can see it there a picture of it on the right. It's on display in Turin. You can go and see it. I've actually seen it. Now, up until 1988, the Catholic Church wouldn't allow it to be tested. But in 1988, scientists were given a small piece of it and they examined it and found that it contained 91% of carbon-14. So let's use our equation to find an approximate age of the shroud. So we're going to use our equation, and you can see how I've substituted in the value for K that we found before. Now, in 1988, the shroud contained 91% of carbon-14. So I'm going to make A 0.91 and A naught is going to be 1. And we're going to solve for T. That's going to tell us how old the cloth is. So taking logs of both sides and then dividing by this number, T is approximately equal to 779.4 years. So could this cloth have covered the body of Jesus? Well, I guess you've got to know when Jesus died, and that was around about 33 AD or ACE, after Common Era. So this is definitely not the cloth that covered the body of Jesus. If I do 1988 take away 779, this cloth covered a body that was killed in the Middle Ages, around about 1209. Okay, let's move on. Now, unlimited exponential growth or decay is not always an appropriate model, particularly if there is another factor that inhibits the growth or the decay. And one of the main applications of limited growth and decay is Newton's law of cooling. And it states that the rate at which a body cools is directly proportional to the difference in temperature between the body and its environment. This is what we can write. So capital T stands for temperature. dt, d little t, is proportional to the difference between the temperature of the body and the temperature of the environment. Now, we sometimes call this temperature here the ambient temperature. Okay, so let's work through and get a solution to this differential equation. Again, we have a linear relationship here. We have direct proportion. So dt dt is going to be equal to K, which is some constant, and then in brackets T take away TA. All right, I'm going to want to integrate both sides with respect to capital T, so I'm going to invert both sides. All right, let's set up the integral. T is equal to, I'm going to bring the 1 on K out the front because it's a constant. Integral of dt over T take TA. Now remember, that's a constant. All right, so this is just going to be a simple log. So T is equal to 1 on K ln of T take away TA plus C. Now, just like we did before, I'm going to take the C over the other side. So T minus C is equal to 1 on K ln, and then T take away TA. Multiply both sides by K, and then raise both sides as powers of E. So I get E to the K brackets T minus C is equal to capital T take away capital TA. All right, now finally let's move this over. Now you can see at the same time I've done my sneaky trick again. I've split this up. So this is E to the KT times E to the negative KC, and that is a constant. So I'm going to rewrite this as A plus B E to the KT. Now A is the ambient temperature, B is a constant, E to the KT, and K is another constant. Here's an example. A cup of boiling hot tea is placed in a room which has an ambient temperature of 22 degrees. After 10 minutes, the temperature of the tea is 82 degrees. What is the temperature of the tea after 20 minutes? Now we could start here with the differential equation and then solve it, and we would end up with this solution. Or, if you recognize this as an example of Newton's law of cooling, you can start here. But just like before, you will have to have memorized this equation. It is not given for you on your reference sheet. I'm going to start here. All right, what do we know? We know the ambient temperature is 22. Now, here's a little trick. A plus B is equal to the initial temperature. Let's have a look at why that is. So I'm going to substitute in T is equal to 0. So capital T of 0 is equal to A plus B E to the 0, and of course anything to the power of 0 is 1. So T of 0 is equal to A plus B. Now we know initially the T is boiling, so that's 100 degrees. That's going to be equal to 22 plus B. Therefore, B is equal to 78. Okay, after 10 minutes, the temperature of the tea is 82. So let's substitute that in. So capital T is 82, little t is 10. Subtract 22 from both sides. Divide both sides by 78. I have 0.76923 is equal to e to the 10k. Now take logs of both sides. I've switched it around. 10k is equal to ln 0.76923. Divide both sides by 10. K is approximately equal to negative 0.02624. And this is a good check for us because this is an example of decay, so our constant should be negative. All right, substituting that in. We want to answer the question, what is the temperature of the tea after 20 minutes? We substitute 20 for t, for little t, and we get 69 degrees Celsius. Okay, let's move on. Now, a logistic equation is a model for population growth, but it has a limitation. There's going to be a natural carrying capacity that's going to limit the population's growth. Now, what does that mean? So if you've got a species that's the population is increasing out of hand, eventually it's going to stop increasing because it's going to run out of food or it's going to run out of space. And you're going to get a curve like this. So rapid increase, and then it's going to taper off as it approaches this carrying capacity. Now here's the equation. The rate of growth is proportional to the population size itself, and then multiplied by 1, take away the population divided by k, which is this carrying capacity. And of course, we can write this as dp dt is equal to kp in brackets 1 minus p over k. Here's an example. It is estimated that the human population reached its first billion in 1804. In 2022, the human population reached 8 billion. Some estimates place the carrying capacity of the Earth at 10 billion people. The population of humans, h, grows according to the differential equation dht is equal to kh multiplied by 1 minus h over k. T is the number of years since 1804. Solve the differential equation. So we're going to let h and k be in billions. So therefore, k is 10. So here's our formula. dh dt is equal to kh multiplied by 1 minus h on 10. Now that's the same as kh multiplied by 10 minus h on 10 because we want to invert both sides of this equation. So dt dh is 1 over kh multiplied by 10 over 10 minus h. Let's integrate. T is equal to 1 over k, the integral of 10 over h multiplied by 10 minus h dh. Now, we are given that 10 over h multiplied by 10 minus h is the same as 1 over h plus 1 over 10 minus h. So let's substitute that in. We have the integral of 1 over h plus 1 over 10 minus h dh. And these, of course, are both log functions. So we have 1 over k, and then in brackets, ln of h, take away ln of 10 minus h, close brackets, plus c. Now we can join these logs together. So we have 1 over k, ln of h over 10 minus h plus c. Now we need to resolve both of these constants, k and c. But we were given two pieces of information. Let's use the first one. This says that in 1804, the population was 1 billion. Substitute it in. C is equal to negative 1 on k ln 1/9. And we've got another two log functions that we can join together. So we've got 1 on k. This is going to be divided by 1/9, which is the same as timesing by 9. So 9h over 10 minus h. Now let's substitute in. 2022 is 218 years after 1804, and the population was 8 billion. Substituting it in, I'm going to take the k over and swap it with the 218, and working that all out, k is equal to 0.0164. Now before we substitute that k in, let's take the k over the other side, and we're going to raise both sides as powers of e. And now I've substituted the k in, you can see that. Alright, let's take this 10 minus h up here, because we want to make h the subject. Expand, and then I'm going to get these h terms together, so I'm going to take this one over this side. You can see I've turned it around. Factorize the h out and divide by 9 plus e to the power of 0.0164t. And there we have h. Now we can further simplify it by multiplying top and bottom by e to the negative 0.0164t. Part B, when will the human population reach 9 billion? Now we could use that formula that we just derived where h is a subject, but because we're wanting to work out time, we could use the formula that we worked out partway through, and it's much easier because we can just put 9 in here. And that's going to give us 263 years after 1804, or in other words, 2067. C. Sketch the graph of h against t. So I've done this using Desmos, but you can see that we start off with an exponential type curve, and then around about here it changes concavity and then tapers off towards an asymptote of h is equal to 10 billion. Part D. When was or will be the population growth a maximum? So we have dh dt, here's our k, 0.0164h multiplied by 1 minus h on 10. We could differentiate this and put it equal to 0 and test that it's a maximum and all of that. But it's just a parabola, and the easiest way is just to find the vertex of that parabola. So it's equal to 0.0164h minus 0.00164h squared. And of course, the maximum occurs at the vertex of the parabola, which is minus b on 2a. So b is 0.0164 and a is negative 0.0164. Substituting it into the formula, we have h is equal to 5. Now that doesn't actually answer the question. We want to know when the population growth was a maximum, so we're going to need to substitute it back into that previous formula to find t. And again, we're going to use this formula where t is the subject, substitute in h is equal to 5, and into the calculator we get t is equal to 134 years after 1804, or in other words, it was at its maximum growth rate in 1938. Okay, this is our last example of applications of differential equations, and it's called conserved quantities. A conserved quantity is where the substance is neither created nor destroyed, but there is a rate of change of the substance due to it flowing in and out of a confined region. And this is how we model it. So with respect to time, we have the quantity Q, and the rate of change is equal to the rate in, take away the rate out. So here's an example. A tank holds 200 litres of a water-based solution and 50 grams of a radioactive substance. Clean water flows into one end of the tank at the rate of 10 litres per minute, and the solution flows out of another pipe at the same rate. But we have a further complication because each minute the radioactive substance decays at a rate of 0.01 times the amount present. Form a differential equation for the amount of radioactive substance in the tank at time t. So let's start with the definition. Let m of t be the grams of radioactive substance at time t. Now this is what we know. In terms of the inflow, there's no new radioactive substance coming in. So the concentration of radioactive material in the inflow is 0 grams per minute. But the outflow is another story. Okay, here's the proportion of radioactive substance that's sitting in the 200 litres at any particular time. And 10 litres is flowing out per minute. So this is an expression for the concentration of radioactive substance that's flowing out in grams per minute. We also know that there's a decay of the substance and it's equal to 0.01 multiplied by however much substance is left. So here is our differential equation. The rate of change of the grams of radioactive substance with respect to time is equal to 0, take away this much, take away this much. And there is our differential equation. Now we just need to solve it. And it's a pretty easy differential equation. We can tidy this up to negative 3m on 50. We want to integrate both sides with respect to m, so let's invert both equations. So dt dm is equal to negative 50 on 3m. Integrate both sides with respect to m, t is equal to negative 50 on 3, the integral of 1 on m dm, and that's of course going to be a log, isn't it? And so it is equal to negative 50 on 3 ln m plus c. Now initially there was 50 grams of radioactive substance, so at t equals 0, m is equal to 50. Substituting that in, we're going to see that c will equal 50 ln 50 over 3. And substituting in for c, this is what I get. And I can join these together because I've got a common factor of 50 on 3. That'll leave me with ln 50 take away ln m, which can be written as ln 50 over m. Right, we want to make m the subject, so multiply both sides by 3 on 50. And before we raise both sides as powers of e, I would like this m to be on the numerator. So I'm going to negate both sides, and that will flip this 50 on m like this. Okay, make sure that makes sense to you. Now let's raise both sides as powers of e. And that will give us this, multiplied by 50, and there's our answer. Okay, just before we finish, let's summarize the different applications we've looked at in this video. The first one, exponential growth and decay. Here's the differential equation, here's the solution, and remember if k is greater than 0, it's growth, less than 0, it's decay. Newton's law of cooling, we have dt is proportional to the difference between the temperature of the object and the ambient temperature, and here is the solution to the differential equation. We looked at logistic equations, and here's our differential equation. Capital K is the carrying capacity. There's the solution. I didn't go through that in this video. I don't think there's any point memorizing it. And then finally, conserved quantity, and that's where dq dt was equal to the rate in, take away the rate out, and the solution in this case will vary. Now I did mention that it's probably worthwhile, in my opinion, memorizing these two, just in case. It saves you having to solve a differential equation. Okay, would you believe it? We have finished differential equations.